In the previous videos, when we drew Lewis dot structures, we drew them without accounting for lone pairs, the electron pairs that are by themselves. We just drew them in a straight line or in a T-shape or a triangle. It's a 3D model of a molecular structure that accounts for a lone pair, so the bonded pairs will be pushed closer together because the pair electron will repel each other. Pause the video, draw the Lewis dot structure for BeH2, CO2, and ClF, and then check your answer. Also, in your notes, if you don't have them, draw the table that is provided below with the proper titles, and we will fill the table as we go along. So Be has 2 valence electrons. There are 2 hydrogen with each 1 valence, so there's a total of 4 electrons. Least electronegative goes in the middle, Be, and it's going to have a hydrogen on each side. Each hydrogen fulfills the duet rule, so it is happy, and if I count, there's 4 electrons. Be and B tend to violate the octet rule. They tend to have less than 8. Usually it's between 4 to 6 electrons because they don't have enough electrons in the valence shell. In addition, they are known as electron deficient, and they look for Lewis dot structures with lone pairs to form coordinate covalent compounds. And later in the year, we will learn some of these will be Lewis acids and bases. Carbon has 4. There's 2 oxygen. Each oxygen has 6 valence electrons, a total of 16 electrons. And we do this many times, and you should have oxygen, double bond carbon, double bond oxygen with 2 pairs of lone pair on the outside. And this was the most stable structure. We also drew the triple single, single triple, and we found that the formal charge was higher. Cl has 7 valence electrons plus fluorine, which has 7 valence electrons. This is total of 14. They have to start with a single bond, and they're right next to each other because there's only 2 elements. Chlorine needs 6 more because it has 2 from the bond, and fluorine also needs 6 more. If you count the electrons around the Lewis dot structure, it matches the valence electrons. So these structures are all correct. All 3 of these structures, no matter how you rotate it, these 3 structures, no matter how I draw them, they will look like a line. Since they look like a line, their electron pair arrangement is linear because it forms a line. Now I'm going to look at the central atom of VeH2. I'm going to look at the central atom of Be. I'm going to count the number of bonds. When we do this, a single, a double, a triple counts as 1. So if I have a triple bond, it is considered to be 1 bonded pair. If I count a double bond, it is counted as 1 bonded pair, and a single bond also counts as 1 bonded pair. Here I have a bonded pair on the left and a bonded pair on the right. So this one, BeH2, has 2 bonded pairs. It has 0 lone pairs because if I look at the central atom Be, there is no lone electrons. We only see bonded. Since there is no lone pairs, my electron pair arrangement here does not account for lone pairs. Molecular geometry counts the repulsion from the lone pairs. Since there's no lone pair, my electron pair arrangement and molecular geometry will be the same. Whenever there is no lone pairs, the electron pair arrangement geometry are the same. Since it's linear or a line, the angle of a line is 180 degrees. My general structure, if you look at it, we have B and then we have A on the outside. So B is your central atom, like BE. A is the outside atoms, like H. If I look at CO2, again, I look at my central atom. We don't look at the outside. We have two bonded pairs. Remember, a double, single, triple count as one. So we have one bonded pair here and another bonded pair here. Two bonded, 0 lones around the C. So this electron pair arrangement is also linear. Its molecular geometry is also linear because there is no lone pairs. And the angle is 180 degrees. When we have two elements together, like ClF, they will always be linear. There is no central atom. Since the two atoms can only be drawn side by side, it will always be linear. Two general structures that you could have for linear, it is ABA, in which the bonds could be single, double, or triple. And then you could also have two elements, AB. So examples of here, you could write BeH2, CO2, and ClF. We will come back to polar and nonpolar and hybridization after we fill the table. Pause the video and draw the Lewis dot structure for these two, and then check your answer. So sulfur has 6 valence electrons plus 3, and oxygen has 6, so there's a total of 24 electrons. Central atom is the least electronegative, which is sulfur. And if I start with a single bond, you realize that I'm going to exceed the octet rule. I need a double bond. If I start with a single bond, I'm going to exceed the octet rule by 2 electrons, and so I know it's going to be a double bond. You drew this in class already. Each of the oxygen need 4 more electrons for the double bond, and the rest needs 6 because it has a single bond to fulfill the octet rule. Sulfur already has 8 from the bonds. This will have a resonance structure, and I'm going to draw all of these by rotating the oxygen and then fulfilling the octet rule. BF3, we drew this one in class 2. It's 3 plus 3 times 7 from the fluorine. This one also has 24 electrons. My central atom is boron because it's the least electronegative. And when we drew it, boron will not fulfill the octet rule. It will have less than the octet. Each fluorine has 2 bonded electrons, so it needs 6 more to fulfill the octet rule. Boron will be electron deficient. It's going to look for Lewis dot structures with lone pairs. Boron can have less than the octet rule. So I'm going to look at my central atom. For SO3, I have 3 bonds. A single, double, triple all count as 1. So we have 1, 2, 3 bonds. There's going to be 3 bonded pairs. If I look around sulfur, there is no lone pairs, so that's 0. 3 bonded pairs and 0 lone pairs have an electron pair arrangement called trigonal planar. Since there is no lone pairs, the molecular geometry is also trigonal planar, and the angle between the bonded oxygens are 120 degrees. Here, oxygen to oxygen is 120 degrees, and here too, oxygen is 120 degrees. If I look at this resonance structure, we still get the same structure. We have 3 bonded pairs because a double bond still counts as 1, so that's 1, 2, 3. There are still 0 lone pairs, so this is still trigonal planar. If I look at the third resonance structure, the same is true. I have 1 bond from here. This double bond counts as 1, so that's my second one. And that's my third one, so it's 3. And my lone pair is 0. If I look at BF3, it is also true. All single bonds, but there's 3 of them. No lone pair, so that is also a trigonal planar. And you could write those down as your example. So the general structure is we have a central atom, B, and we have A, are the atoms on the outside. The atoms on the outside might be the same all oxygen, all fluorine, or they could be mixed. And remember, the bonds can be a single or a double. Pause the video, draw the Lewis dot structure for SO2, and then check your answer. So sulfur has 6 valence electrons. 2 oxygens each have 6 valence electrons, total of 18 electrons. Sulfur has to be the central atom because it is the least electronegative. And if we start with a single bond, central atom is going to be sulfur, which is the least electronegative. I'm going to start with a single bond. Each of the oxygen needs 6 mores because it has 2 from the bonded to make 8. Sulfur has 4 from the bonded, so it needs 4 more electrons or 2 lone pairs. And if I count 20 electrons, so the Lewis dot structure has 20 minus 18 from the valence. There's 2 extra electrons. So that means one of the oxygen will have a double bond. Oxygen. The oxygen with the double bond needs 2 pairs of electrons. To fulfill the octet, the one with the single bond will need 6 to fulfill the octet. And the central atom, sulfur has 6 from the bonded, so it needs a lone pair. So this is the correct structure for SO2, and this will have a resonance structure. And so the oxygen could go on either side with a double bond. If I look at the central atom here, it has 2 bonded. Double bond counts as 1, and the single bond counts as 2, so that's 2. And it has a lone pair, so there's 1 lone pair. If I look at the other structure, same thing. I have 1 from the single bond, 2 from the double bond, so that's 2 bonded pair, and it has a lone pair. For the electron pair arrangement, we do not account for the electron-electron repulsion from the lone pairs. A single, a double, a triple, a lone pair counts as 1. So if I look at my bonded pair and the lone pair, 2 plus 1 equals 3. If I look at the row above, 3 plus 0 equals 3. Since it doesn't count for the electron-electron repulsion from the lone pair, electron pair arrangement is also trigonal planar. However, the molecular geometry accounts for the lone pair, so it cannot be trigonal planar. The lone pairs will repel, and if you look at the structure I drew, it looks bent or angular. So the molecular geometry is bent or angular, one or the other. You don't need to do both. And my angle is going to be less than 120. These lone pairs repel. This angle between the oxygens will be less than 120. And you just need to memorize it is less than 120. So the general structure for 2,1 trigonal planar is going to be central atom B. We're going to have 2 atoms on the outside. The bond could be single or double. And we're going to have a lone pair. In addition, if you do enough Lewis dot structure, you will recognize patterns. So for example, SO2, it has 3 elements. The total valence electrons equal to 18 electrons. When you draw the Lewis dot, you will have a double single and a lone pair. If you look at SO3, it adds up to 24 electrons, and it has 4 elements, and you have a central atom, and you have 3 on the outside. This will always be singles, double, single, trigonal planar. Pause the video, draw the Lewis dot structure for the following 3 given, and then check your answer. So carbon has 4 valence electrons, plus 4 hydrogen, each with 1, so there's a total of 8 electrons. Carbon has 4 valence electrons, plus 4 hydrogen, each with 1, so there's a total of 8 electrons. Central atom has to be carbon because hydrogen can only make one bond. All the hydrogens fulfill the duet rule, so they're happy, and the carbon has 8 electrons, so it's happy. If I count, it matches the valence electron, so it is correct. Sulfur has 6 plus 4, and then 6 from the oxygen. And we have to add the 2 electrons because it has 2 extra because it's a minus charge. This equals to 32 electrons. Central atom is going to be sulfur with oxygen on the outside. Each of the oxygen needs 6 more because it has 2 from the bonded. Sulfur already has 8, so it's happy. And if I count, the total valence electron equals to 32. And since it's an ion, we need brackets with a charge. In the previous video, we said this structure is not as stable as the 2 double bonds with the oxygen. However, for high school chem, you're okay if they're all single bonds and they fulfill the octet rule. I will take it, unless it asks for all possible resonance structures and formal charges. Then you need to draw all the possible ones for sulfur. Nitrogen has 5 valence electrons. There are 4 hydrogen, each with 1. Since it's a positive ion, we have to subtract an electron. So there are 8 electrons. Central atom has to be nitrogen because hydrogen can only make one bond. So the hydrogens are going to spread out. It fulfilled the duet rule, and nitrogen has 8. If I count the number of electrons in the Lewis dot structure, it matches the 8 valence electrons. Since it's an ion, we put brackets and a charge on the outside. So if I look at my central atom here, for carbon, there are 4 bonds, no lones. For the SO4 2 minus ion, same thing. There's 4 bonds, no lones. And ammonium ion also 4 bonds, no lones. So the general structure of CH4, SO4 2 minus, and NH4 plus, we have a central atom and we have 4 atoms surrounding it. These atoms could be the same atom or they could be different atoms. We have 4 bonded pairs. Lone pairs, there are none. The electron pair arrangement, we don't consider lone pairs, so it's just the things around it, and we said a single, double, triple, and lone pairs count as 1. Since there's 4 total, this takes the shape of a tetrahedron, or it is tetrahedral. Since there is no lone pairs, the molecular geometry which accounts for lone pairs will be the same. The angle will be 109.5 degrees. In general, we draw the structure as 2D. The correct way to actually draw it is any elements in the front. We have a triangle that is darkened in, and we write the bonds. Anything within the 2D plane, we leave it as is with a line. And anything that is back, we draw with dashed lines. Since this takes so much time, we will not be drawing the structures this way. We're just going to draw it with lines. Pause the video and draw NH3 and SO3 2 minus, and then check your answer. Nitrogen has 5 valence electron, plus there's 3 hydrogen, each with 1, total of 8 electrons. Nitrogen again has to be the central atom because hydrogen can make only one bond. So the hydrogens all have the duet rule. The duet rule is fulfilled for the hydrogen. Nitrogen has 6 electrons from the 3 bonds, so it needs 2 lone pairs, and it fulfills the octet rule. And if I count, the Lewis dot structure electrons match the valence electron. The sulfide ion, we have 6 valence electron from the sulfur, 3 times 6 from the oxygen. Since it's a negative, I need to add the 2 extra electrons. And if I add this, this is 26 electrons. Central atom has to be sulfur least electronegative. The oxygens are going to go on the outside, all with single bonds. The oxygen currently has 2 electrons from the single bond, so it needs 6 more. Since all the oxygens are the same, they all are going to need 6 more. If I count around sulfur, it has 3 bonds, which is 6 electrons, so it needs 2 more to fulfill the octet rule. And if I count, it adds up to 26, so this is the correct structure. And we need brackets because this is an ion. Here, the sulfide ion can also have double bonds because sulfur can exceed the octet rule. So we could have something like this. The double bond oxygen needs 4 more electrons or 2 lone pairs. The single bond oxygen needs 6 more to fulfill the octet rule because it only has 2 from the bonded. And if I look around the sulfur, it already has the full octet. However, we need 26 electrons. So the extra electron will go to the sulfur. Since this has a double bond, this can also have resonance structure. We could rotate the double bond to the bottom oxygen, and I fulfill the octet rule. Or it could go to the oxygen on the right, and we fulfill the octet rule. And all of these are possible resonance structures. We could check which one is the most stable structure by calculating the formal charges. General formula of formal charges, formal charge is equal to the valence electron minus the non-bonding electrons or the lone electrons minus the bonded electrons divided by 2, or you could write this as the number of bonds. If I calculate the oxygen, oxygen has 6 valence electrons minus they all have 6 electrons that are not bonded. So that's minus 6, and they have 1 bond. So oxygen has a charge of -1, and all the oxygens are the same, so it has a formal charge of -1. Sulfur has 6 valence electrons. It has 2 lone electrons right here, and it has 3 bonds, or you could do 3 bonds, which has 6 electrons divided by 2, which is 3. This is equal to a +1. For the bottom one, oxygen with the double bond is going to have 6 valence electron minus 4 lone electron. There's 2 on top and 2 on the bottom, so there's 4. Minus, it has 2 bonds, or it has 4 electrons divided by 2, which is 2. This equals 0. We're going to do the oxygen with the single bond. It has 6 electrons minus 6 lones because 1, 2, 3, and it has 1 bond. This is a -1. And then the sulfur is equal to 6 valence minus the 2 lone minus the 4. We have 1, 2, 3, 4 bonds, 0. The top one, the oxygens all have a minus charge, and the sulfur has a +1 charge. For the bottom structure, they're all going to be the same. All the double bond oxygen are going to have a 0 charge. These are all 0. The oxygen with the single bond is going to be a -1, and the sulfur is going to be a 0 charge. So if I compare the top and bottom, the bottom structure is more stable. The formal charges are close to 0 or are 0. The more electronegative element gets the minus charge. On top, even though the oxygen, which is more electronegative, gets the negative charge, least electronegative sulfur gets the positive charge, none of the formal charges are 0. So the bottom structure is more stable. So on the test, I will accept the top Lewis dot structure unless they ask you to write all the possible resonance structure and calculate the formal charge. If it does not ask you to calculate the formal charge, you could use the top structure. If it asks you to calculate the formal charge, you need to draw all the possible structure. Sulfur with the double bond, a lot of these are discovered by experiments. We know sulfur can exceed the octet rule because it has empty d orbitals, but even a lot of the scientists did not know they'd like to have double bonds. For college, you need to do the correct structure. So if I look at my central atom, sulfur, and it doesn't matter which structure I look at, I could count the number of bonded and lone pairs. A single, double, triple, lone pair counts as one. So if I look at this top structure here, we have 3 bonded pairs and 1 lone. Here are my 3 bonded, 1, 2, 3, and here's my lone. If I look at my bottom structure, I have 3 bonded, 1 lone. This is 1, 2, 3 bonded, 1 lone. This one too. 1, 2, 3 bonded, 1 lone. 1, 2, 3, 3 bonded, 1 lone. And if I look at NH3, same thing. I have 1, 2, 3 bonded, 1 lone. So we have 3 bonded pairs and 1 lone pair. The general structure of this is B is my central atom, and we have elements on the outside. Again, they could be single, double bonds, and we have a lone pair. So we have 3 bonded, 1 lone. Electron pair arrangement does not account for the lone pair repelling each other. Its arrangement is tetrahedral. 4 plus 0, there's 4. 3 plus 1 is 4. The bonded pairs plus the lone pairs add up to the same number. They have the same electron pair arrangement because it does not count for lone pairs. However, the molecular geometry will be different. The lone pairs will repel and push the bonded pairs closer together. So the shape for this is trigonal pyramidal. And since the bonded pairs are closer together, my angle is going to be less than 109.5 degrees. Pause the video, draw the Lewis dot structure for these two, and then check your answer. Hydrogen, there are 2 of them, each with 1 valence plus 6 from the oxygen. This is 8 total electrons. Central atom has to be oxygen because hydrogen can only make 1 bond. Hydrogen fulfills the duet rule. Oxygen is deficient 4 electrons, so we have 4 electrons or 2 lone pairs. If I count, there are 8 electrons in the Lewis dot structure, which matches the valence electrons. Sulfur has 6 plus 2. Chlorine, each with 7 valence electron, which is 20 electrons. Central atom has to be sulfur because it's the least electronegative. Each of the chlorides are going to go in opposite side. Since it has 1 bond or 2 electrons, it needs 6 more each. Sulfur has 2 bonds or 4 electrons, so it needs 4 more or 2 sets of lone pair. If I count, it equals to 20 electrons. So this is the correct structure for SCl2. If I look at the central atom of water, there are 2 bonded pairs and 2 lone pairs. If I look at the central atom sulfur, I have 2 bonded and 2 lone. So the general structure for 2 bonded pairs and 2 lones is we have central atom B. We have 2 elements on the outside. We have 2 lone pairs. Electron pair arrangement does not account for lones. 2 plus 2 is 4, so my electron pair is still tetrahedral. We have 2 lone pairs, so there's going to be a greater electron-electron repulsion. So my geometry is bent, angular, or V-shape. You only need to memorize 1, and the angle will be much less than 109.5. This is a summary of the tables. First thing you want to do is count the total number of valence electrons correctly. Least electronegative element go into the center. You will realize if you draw the resonance structures correctly, no matter which one you use, you will still get the same answer. Always count bonded pairs and lone pairs correctly. A single, a double, a triple, and a lone pair, they all count as one. When you have two bonded and zero lone, it's linear like a line. Its molecular geometry is linear, and since it's a line, it's 180 degrees. If we have three bonded and zero lone, this is trigonal planar. Since there is no lone, the molecular geometry and the electron pair arrangement are the same. The angle between the bonded pairs are 120 degrees. If we have two bonded pairs and one lone, the structure will have a lone pair. Since electron pair arrangement does not account for electron-electron repulsion, 2 plus 1 is 3, so electron pair arrangement is still trigonal planar. The molecular geometry due to the lone pair will be called bent or angular, and the angle will be less than 120 because the lone pairs will push the bonded pairs closer together. When the bonded pair and the lone pairs are 4 and 0, that is tetrahedral. Since there is no lone pair, molecular geometry is also tetrahedral. The angle is 109.5 degrees. When we have 3 bonded and 1 lone, the electron pair arrangement is still tetrahedral because they add up to 4. The lone pair pushes the bonded pair closer, so the molecular geometry is trigonal pyramidal or trigonal pyramid. The angle will be less than 109.5. When you have 2 bonded and 2 lones, 2 plus 2 is 4, so this is also tetrahedral for the electron pair arrangement. However, the molecular geometry will be bent, angular, or V-shape. You only need to memorize one of the 3, and the angle is much less than 109.5. So you have to memorize this table for the test. This is part 1 of the video. The second video will exceed the octet rule.